Okay, so so far we've been working with linked lists a lot, doubly linked lists, and using that for stacks, for queues. Now what we're going to be doing is working with trees, another type of structure. Now we're going to be doing a lot of different type of trees. Now we're going to be focused on one type of tree, which is these binary trees. Why does it? Okay, now it starts. So let's talk about those trees. And before talking about the trees, we need to talk about this comparable interface. You remember the comparable? The what? No, no, not the iterable. No, the comparable. Exactly. It has just one method. It's an interface that has one method just compare to. If you remember, the compare to just allows you to compare between objects. Like you have less than, greater than, something like that. Because how can you compare between two students? Which one is smaller than the other? We don't have that unless you implement, this student implements comparable. Then you put some code that shows how these, one student can be smaller than the other one, or another one bigger than the other one, based on the criteria that you put there. So this is important because in the trees, we're not going to be putting some values randomly, as in a tree, in the representation of a tree, but we can just sort them somehow. And this is why the comparable is going to be handy. So we're going to use that. So the comparable basically just says, we'll just have a look at it. Remember, it's going to be used. But what we're going to be doing mainly is just talking about the trees and the values inside of those trees. When we sort them, obviously we cannot sort them unless the nodes of those trees are comparable. So we're going to be doing something like that. In the code, you're going to see something that refers to this comparable. So anyways, there's a lot of different kind of terms. The root is the first parent. The leaves are the ones that has no children. But the idea is that this is like a tree. This is an empty tree. Well, there's nothing. But this is a tree and this is another tree. But this is the root, which is the one on the top. And the one on the bottoms are the leaves. So, and we also have the path, which is the one that takes you from the root until the leaf, or the length, which is how many nodes do we cross in that path, and the level that tells you, I mean, how many levels do we have. If we have like some kind of nodes on the same level, so this is basically what we mean, just say those that are on the same kind of level. And the height is the maximum number of levels. So that's the height. So I mean, there's some kind of words, we're going to see them, we use them later on, but these are different type of trees. What we're going to be looking mainly in and using are binary trees. But let's talk about them later. Now the representations of those trees, as you can see, like this can be a tree. What is what? The level is like, for example, when you said like two nodes are on the same level, when they have like the same distance from the root. So that's the kind of level. So for example, these are all the same level. Yeah, so that's what basically, how can you, I mean, define that is how far they are from the root, for example. They have the same distance in terms of how many arcs they cross.
So how can I know which levels are the nodes?
By counting this from the root, for example, by counting how many nodes you have to go through before reaching it. Then this is how you can know the levels.
So the root becomes 0 or 1?
I'm sorry?
The roots become level 1 or 0?
The root is level 1. Level 1. Yes. The root is level 1. level 1, level 2,
It has a four
level 3, level 4. This one has 4 levels. Yes. And generally we are going to be working with ordered trees when the values are in some kind of an order. And well, generally we use two types of representations for the trees. We can represent trees in arrays or in using linked lists. Same old discussion that we have. But we're not going to be focusing too much on the array representation of a tree, because of really it's not really as intuitive, and for also the main reasons of if you'd like to insert something in the middle with the arrays, it's not efficient. So we're going to be working more with lists, and we're going to represent that and see those lists as a tree. But what we're going to be doing is not like any kind of tree. We're working on binary trees, and those binary trees are special trees that do not have more than, every node has only maximum 2 children. So there's a node, and the node has a parent and has the children. So this is a binary tree, which means maximum 2, and that's what we're going to be working with. But notice also, we're not going to be put them in a way that is just random. It is going to be sorted. You see, for the node, the one on the left is smaller than the node itself. The one on the right is bigger than the node. So the children of a node are going to be sorted based off, if they're smaller, we put them in a way on the left, to the left. If they're bigger, we put them to the right. And the binary tree, well, we have this kind of recursive definition because it's a tree that is either empty or it is made of a single node consisting of a data value and 2 references, left and right, for each pointing to a binary tree. So a tree is composed of binary tree. When you see this, that means we're recording a video, and it just came and crashed my video with your talking to Yazid. You're sorry? Okay. You're sorry. He's sorry. So, we said that this is kind of like a recursive definition of a tree, because a binary tree is a tree that each node can be also a binary tree, because a binary tree can be either empty or it has 1 or maximum 2. So anyways, that's not there's some kind of other type of terms that we use. A complete binary tree, yes, that means there's no empty nodes. Everything is complete. Anyway, so there's a lot of different kind of trees. I mean, this is a decision tree, is by which all nodes have either 0 or 2 non-empty children. This is called a decision tree, like this one, for example. It's like a binary tree, but we don't have like one that has only 1 child. It's either they have 0 or 2. That's this decision tree.
So in the previous slides, previous one.
This one?
Not a decision tree.
This is not a decision tree, because it has one of the nodes, like this 9, has only 1 child.
So it has a certain name.
This one, binary tree. Like binary tree is most general, and then like decision tree is a kind of specific, a special type of binary tree. Yeah. And they come with some kind of relationship between non-terminal and terminal. But anyways, I don't want to talk. I'm just telling you that there's a lot of different kind of trees. That's what I'd like you to focus on right now. But what we would like to be focusing on and working with, what we're going to be doing a lot, and the focus of this week's class is going to be on using binary trees and how to search within those trees. So this is what we're going to be doing. Binary search trees, basically because we would like to make sure that they are ordered, and there are also some kind of balancing. We don't want to have like some kind of like all the nodes that are in one side, so we'd like to have some kind of balancing, because we'd like to spend the least amount of time trying to find a number. And to do that, it's better if we have it in a tree that is kind of balanced somehow. Because now if you're looking for a number, let's say if I'm looking if 5 exists, I can just ask maybe 2 questions and I can find if 5 is there. The first question, is this 5? No. So it's less than 5? Yes. Okay, go to the left. This is greater than 5? Yes, so the 5 should be to the left, so I'm going to go. And is this 5? No, going to the left. Well, there's no more left, so that means just after this I can so know that 5 is not available. And imagine there's a big tree and then I'm have to look for a number. It's much easier to do that with this binary search tree. So that's the main idea why we're looking into that, because we'd like to be able to find things faster. So now let's have a look at how we implement that. So we said that there's an implementation that can be done using an array, but it's kind of complicated. Just have a look at this. If I'd like to use this array to implement this as an array, I need to have 3 arrays actually. One for the value, one for the left, one for the right. And how do you see that? Well, I'm just for fun. I know that you like these kind of numbers, so just to give you an idea actually how to understand that. So 13, this is the value as index 0. So the values are just stored as they are entered, and then this, it tells me which one is the left, which one is the right. So for example, this is my array with all the values. So you ask the user, for example, to give you the values, you just put them. But then when you put them, you organize them in a way that they are sorted like this. So, for example, 13. On the left of 13, what is the other number? No, what is, no. Just saying here, this number is 10. Okay, 10, what's the index of 10? So that's why I'm putting here, on the left of 13, the value is found at position 4. And on the right, so 25. What is 25? So I found at the position 2. So these are indices of the values on the left, indices of the values on the right, of each one of them, that each information that is here. So for example, if I look at this one, 12. What's on the left of 12? Nothing. One of the right? Nothing. So that's how this is represented. So you can see this some kind of complication because you have to maintain 3 different arrays. And if you move something around, you better not get confused because you might mess up the whole thing.
But Victor, how can I order this? It's not ordered.
It's stored now, not ordered, right?
Yeah.
But if, for example, I'm going to move to something, I'm going to look at the indices. I look for the index. I'll start from 0. This is the 0 is the root. And then, okay, after 13, is it greater than 13 or less than 13? If it's, for example, I'm looking for a number greater than 13, I'm going to look to the right. What is the other number? I'm looking at the position 2. So I'll jump to 2 and see now here. Is it greater than, so what's the number I'm looking for? Is it greater now than 25? Yes. So go to the right again. Which one is the right? So 1. So then this is here. So this is how it works.
So index 0, 0, 1, 2, it's by their ID.
Now this one are just indices of these 3 arrays. We have 3 arrays, each one for these things, and these are, each array has an index, right? Each element has an index. So that's what the index is. So we have these different values. So this is 0, this is 1, 2, 3, this is 0, 1, 2, 3. But this is the index of that. But I'm just, so when I'm talking about this index, I'm just focusing on the index of the info. But each one of them basically has a different index. But it's not pay too much attention to it. I just want to show you the complication that this has, and it's not really that intuitive, as opposed to also on top of that there's a problem with what if I'd like to insert something new in the middle, and it's not, anyways, it's not going to be easy to maintain. So this is the other way. And notice here, now we're not accepting any node. The only node that we accept is a node that is comparable. You remember this comparable, right? So by doing this extend, you remember that we can put some conditions on these generics. So this data type, I'm not accepting any data type. I'm accepting only data types that are comparable, that are children of this. Do you remember this? Or we've used that, right? This extend, I'm talking about this extend. So what does this mean? It means that this class can accept any data type as long as it is implementing comparable. So that's the idea. And basically, let's just jump to some of the things. Well, I'll get to those later. Now, how to move now using those list representations of those things. We're going to be using these lists. We're going to go back to that and implement that in a minute. We're going to be using that in the code, but I don't want to go to the code for now because I'd like to just understand the concept first, how they work. Now, if I'd like to, for example, go to visit every node of a tree, notice again that what we have here is a binary tree, right? And it's sorted, as you can see. Well, this is now letters, but I can sort letters. A is smaller than B, which is bigger. B is bigger than C. Really? C is bigger than B, right? But A is the smallest. Why? Because they said so. And also, if you remember, something that we've seen some time ago is this ASCII table. Remember the ASCII table? Yeah, because every character, actually different character has a number. And the first one is A, 65, B, 66, C, 67, and so on. And the capital letters are smaller than the lowercase. Because when you compare 65 is smaller than 97. So anyways, now this is sorted. Now there are different ways now how to look and traverse every node in a tree. There's some method that is called breadth first, and another one that's called depth first. So how does the breadth first work? The first thing is that you start from the root all the time. So that's why this is the first thing that I'm going to visit. Then I'm going until I reach the child. So that's why this goes here. I'm going to go to the smallest first until I reach the smallest child, and then I'm going to move out to the biggest child. And it's called breadth first because you're just going to do this. I'm sorry, I said wrong. I was explaining something different. This was depth first. We're going to go to the children. I would like to go for a level by level, basically. Go to this one, finish this level, then go to this level, including the 2, then go to this level, and then the children, the last one. That's why actually this is the breadth first, and what I was explaining is something else. So that's why when we would like to do this, check this one, then the D and L, then after that B, F, J, N, B, F, J, N, and then we have A, C, E, G, I, K, M, and O. So basically the breadth first, you're just looking for the levels. The other way is to have this depth first, which the depth first is, I mean, you have to go till the different nodes first. So, but in order to, for me, so I go to the H, and I start from the root, then D, then B, then I reach this A. That's why I have this H, B, D, B, A. But there are different ways when I'm going to do that, and that's what I'm going to be talking about. So let's just go back now and look at this breadth first. How do we implement something like that? This is an example of the implementation of a breadth first. How can I have something that is going to be breadth first? So I'd like to look into that and make sure that we understand how this works. So we have this to be, P is the one that is going to be our root. That's where we start. And we use a Q. Why we use a Q? It's first in, first out. And let's see why actually, because for now we don't see why is it, why does it have to be Q? But let's have a look now. The Q basically is if I, it's not like a stack. This is if I do something like this, it looks like more like a stack. So what I'm going to do, I'm just going to represent a queue with, I mean, something like maybe like this. So it enters and then it gets out. If the first one to enter is the first one to get out. So now we start with P. This is the root, and then we initialize the queue, and then as long as it's not null, the P here is what is going to be moving to from one to another. Let's see. We're going to enqueue P. So we start from, sorry, we start from here. We're going to enqueue P. So this is where P is, which means we enqueue H now. And then, while the queue is not empty, the queue is not, okay, I have to remove my hand from the control tab. So while this queue is not empty, the queue is not empty, I'm going to dequeue. So that means I dequeue this, that means I'm going to display this thing. When I'm dequeuing, I display it. And then what next is going to happen, I visit P. What does this visit P? I need to stop moving around, so I don't. I will just, you know, I need to find a better way. Hold on. I'm going to do something different. Discard. Yes. I'd like to have this separated from this. And I have to them both in. And yeah, let me just do this. I'd like to open these two together so I can see them both. Okay. All right, so we were here. Okay, now, oh, that's not right, because this is kind of, Why is it?
Backwards.
All right. Can I open it twice with PowerPoint? No. Okay. So I'm going to do it a different way. This is like this, and this is like that. Now I'm just going to make use of this. This might be better. Okay, because I will also get my pen here. So now let's get started. We have, this is our P. So P points to this root. That's what we do. Then we have our Q. We represent the Q to be something like this. And the first thing that we did is that we look for this P is not null. It is not null. And then we enqueue P. Then we're just going to enqueue this H. Now, after dequeuing, that means we dequeue and put it in P again. So that's what we did. P we dequeued, so we removed from the queue, and then P is still, this is now this value. This we visit it. The visit means we're going to, let's say, display it. And then we look, is the left not null? It's not null, the left. So what I'm going to do, I'm going to enqueue the p.left, which means now I'm going to enqueue D. And then, is the right not empty? The right, is it not empty? Well, yes. So I'm going to enqueue the right. I'm going to enqueue the right. So this was dequeued, right? That's why, and then I visited, I displayed. But I enqueued the left, then enqueued the right. And then what is going to happen, I'm just going to go up in the while. Is the queue not empty? Yes, the queue is not empty. So I get inside, I dequeue. What am I dequeuing? The D. So now I'm dequeuing the D, and then I'm going to put the D into the P. Because when I dequeue, I put it in P. Now my P here is not here. P now is here. So when I'm dequeuing, I'm going to remove it. And I'm going to visit now P. Visit P means I'll display it. Then what is going to happen is that I'm going to check if the left is null. Is the left null? No. So I'm going to enqueue the left. I'm going to enqueue B. And then the right, is it empty? So if the right is not empty, I'm going to enqueue the right. So then I enqueued B, I'm going to enqueue F. And then what is going to happen is the queue not empty? Yes. So I'm just going to start again, go up. I'm going to dequeue and put my P now. I'm going to dequeue this L. This L. I'm going to, my P is going to be pointing here. Notice that the queue has this B and F, which is waiting. Just they're waiting in line because the next thing after finishing these, I'm going to dequeue here. But now if I get in the P, is the queue not empty? No, we just dequeue and then put it in P. So that's what we did. Now this is the L, we visit it. Then we check if the left is not null, then we enqueue it. The left is not null, we enqueue it. So we're going to enqueue this J. The right is not null, we enqueue it. We enqueue this N. And then we just go up again. Is the queue empty? No. Then we just going to dequeue and put it. Now P is going to be here. And this is how you can see that it moves from one level to another. And it just removes, remembers what are the next things that we're going to check. So after this B, I'm going to enqueue now the A and C, so they're going to be there in the queue. But when I'm dequeuing, I'm going to dequeue F, and dequeue J, and then dequeue N, and this is how I'm going to check, doing the breadth first. one level at a time. Yes.
So for the P, every time we assign it to the first element in the queue,
Yes.
that,
When we dequeue, yeah, the first element of the queue, we dequeue it, and this is going to be our P, and we use it just to check the left and right to enqueue them. And when we reach the leaves, like there's nothing to enqueue, for example, because when this becomes this P, is it P dot left, is it different than null? No, it's not different than null, so I'm not going to enqueue anything anymore. So at some time the queue is going just to be dequeued and empty, and that's it. And when the queue is empty, I just leave. And what I have done, I would have just visited each one of the nodes one level at a time, from the left to the right. If I would like to do from the right to the left, for example, if I'd like to display H, L, D, N, J, F, B, etc., what should I do here?
swap the F D left, make it D right, and D right make it D left.
So these two
Swap.
should be swapped. I start from the right and then the left, then this way I'm going just to start from the right. I enqueue from the right, which means I'm going to start from the right. And that's the main idea behind this breadth first and how we implement it. Is that okay? Yes.
It's no problem if we left to start or right or swap it,
What do you mean?
because the breadth are moving with levels, so no
Yes.
problem if this come first or this come first.
You're talking about from the left to the right or from the right to the left? No.
No problem.
But again, when I said no, it depends on what you'd like to do. But you always need to remember that on the left is smaller than the one on the right. That's the idea. But then what you'd like to display, how you'd like to display it, it's up to you. Yes. What? Visit P? Visit P is the one that allows us to display, for example. If you just maybe rename this visit by display. Display P, just going to display it.
Yeah, just like a method.
It's a method that just displays. That what I would like to do with that. When you're here, what you'd like to do, display or do something else. So that's what the visit. Well, of course, this should be defined. Visit P, then what you'd like to do with this, generally visit P might probably just be display system.out.print p.info, for example.
You can like change it to system.
We can change this to system.out.print p.info, for example. But the main idea is, it's kind of convenient to use the queue because when I'm checking something, I unqueue it, like for example the children, and then before finishing I'm going to just, because I unqueued this one on the left, one on the right, and then when I'm going down, I just remember the order where I just unqueued things, and the queue is the one that I would like to use, not a stack, for example, because I would like to keep track of which one was unqueued first, because I would like to dequeue it first. And this is how I can get this kind of result with this spread first. Now, if I'd like to go into this depth first, there's some kind of different ways how to do that. So this depth first, then it starts from the left or from the right. Basically, same idea like with this breadth first. And then we just try to reach as far away down until we reach the leaf, until there is no more where to go. And there are different methods how to do that. They call them pre-order, in order, or post-order. And they refer to them with this kind of VLR, LVR, and V. No, this one.
What's the difference then between pre-order and post-order?
I'm sorry?
What's the difference between?
No, there's a mistake here. Because this is the post order is LRV, not this one, let me just discard that, and I just would like to okay, hold on. The main thing is, when do we visit? You see, this V stands for visit. L, go to the left. R, go to the right. So do we visit, then go to the left, then the right? Or do we go to the left, then we visit, then we go to the right? Or we just go to the left, and then the right, then we visit? What does this mean? Well, let's have a look at this. Now, this is the pre-order. We visit first, then the left, then the right. So we're in a node. We start with the head, with the root. We just visit. Then we go to the left, and when we go to each node, the first thing that we do is that we visit. So we go here, we visit. Then we go to the left, and then here we're in the node. The first thing we do, we visit. Then we go to the left. Then we visit. Then we go to the left. Then we visit. When we go to here, now we need to visit. After visiting, we need to go to the left. There's no left. Okay, go to the right. Or there is no right. Okay, then we are done. Go back. Now we were here, we visited, and we went to the left. What is remaining? Go to the right. So I'm just going to the right, and that's what I'm going to see, the C. Same thing, go to the left. There's no left. Go to the right, no right. Okay, just go up, and then we're finished going to the right here. What do we need to do? We just go up here. And then this, we just visited and went to the left. Then I need to go to the right. So when I go to the right, the first thing I do, I visit. So, and then go to the left. Then I visit and go to the left, nothing to do. Okay, then go to the right, nothing to do here. Okay, go back. We visited, we went to the left, we need to go to the right. We went to the right, we visit. And then same idea, as you can see. Now, it looks like something we've been using like recently.
Stacks.
Not really. It's, yeah, stacks, but stacks of different calls when we're using recursion. When we're doing something, then when we come back, we just continue from where we left off, and then we just continued. And that's the type of things, type of implementation of the pre-order. You see, we visit, we pre-order, call it again with the left. So, and then we pre-order again with the right. So, because the first thing that we did, we visit, then go to the left, then go to the right. Which basically, if we do this, you look at this implementation, as long as it's not null, what we do, we visit, that means we display, then we call the same method again, we go to the left. And the first thing what we do is that we visit, if we go to the left, but when there's nothing else to do, okay, that's done. We just roll back and then continue. So we went to the left, now we need to continue and then go to the right. So recursion is kind of very interesting to do these kind of traversals. So, and this is now this, hold on, where am I? Pre-order. And why is it pre-order? Because look at the result. H, D, B, A. So I just go up, down to the left to display them, and then once I'm here, I'm just displaying the ones on the leaves on the left side until there's no more leaves, and then I just go back to the ones that are next to it. So I'm displaying this one first, 2, 3, 4, 5, then 6, 7, 8, 9, 10. No, I just got to go down. 11, 12, 13, 14, 15. So that's the pre-order. Now in order, if I'd like to have the order, check what is going to be the result of that. And then what I need to do is, you just call the in order, you go to the left. When you cannot go to the left, then you visit. And when you're visited, you just go to the right. And let's just see this, how this is going to turn out. So I go to the left, so I'm here. Go to the left. Okay, there's a left, okay, go to the left. There's a left, go to the left. There's no more left. So I visit. Then go to the right, but there's no more right. Okay, so just go back. So I went to the left. I did not visit though when I was here.
So visit, then visit.
Now I need to visit.
Then you go right.
And then when I'm visited, I just go right. And when I'm going right, I need to go to the left, but there's no left. So I'm just going to visit. Go to the right, there's no right. I meant here. Then what is going to happen?
Go back.
So now let me just do something. Each one of them has to be L, V, and R, right? Because I have to go to the left, to the visit, and R. I'm just going to represent it this way so we just know what we do. So here I go to the left, and I go to the left, I go to the left, I go to the left, then I visit, and there's no right, so I'm just going to call the right, and then
Go back.
I go back here, I need to visit,
Then
that's why, and then I have to go to the left, there's no left, I visit, then there's no right, and then I go up. Now what is remaining here, I need to go, well, I just forgot to put it, I got to go to the right. Now when I finish here, you see this, I just went to the left here, I still need to visit this,
then go right.
so I'm visiting, then I need to go right, and then here I need to, the first thing is go left, there's no more left, so I'll just visit, then go to the right, there's no right, so I'm done. So when I'm here, now I need to visit, and go to the right, and then here I go to the left, there's no left, visit, and then go right, and you can see that now this is done. I'm just back here where I need to visit now. And then I go to the right, which takes me here, left, and visit, and there's no right, and then I'm going to visit, and you can see this how this works. So the idea is representing them with this recursion. First of all, they're easier to read and also easier to follow, and this is basically what we'd like to do. So this is the pre-order. We start by visiting, go left, then right. In order, left, visit, right. And post-order, you left, right, then you visit. Basically, you go to the left. So let's say left. Okay, there's no right, so then I'm visiting. Then I'll go up. I need to go right now. So go right, left, no left, right, no right, visit. Okay, visit, then go back. Here, what is remaining? Visit. Then go up. I need to go right now. Okay, go right, left, there's no right, just visit. And then now what is remaining? What's next here?
Right.
Right, and then left, right, there's no left, right, and then I'm going to visit. And then what is remaining here is the visit. Then what's remaining here is the visit. Here, go to the right, and so on. So you got you got it how it works. So all these are different ways. These are the three different ways how you're going to go from the depth first. Just going down. There's different ways how you can do that. And we've seen the pre-order, in order, and post-order.
So
Yes.
each one of them, if you ask me to by this first, each one of them I can use anyone.
Well, each one of them is a way how to go down. Basically, you just don't go down like that randomly. You have something, you have like a reason for doing so. But the main thing, for example, is that you see the in order. If I'd like to display them all in order, then this is how we're going to do it. Now this thing here is going to be displaying what? What's the difference between this post order and pre-order? Now check the results. So this gives me AC, BE, AC, then B, E, G, and then F. Well, it depends on what you'd like to do. Well, I'm not sure now. That's not clear what this is going to be useful for. But I'm just to show you in theory what we can do with it. But the one that is clearly, we know exactly what we do with it is this in order, because it just displays everything in order. So you can see that's like the sorted from the smallest to the largest. But I would like you to know that there are different ways, yes, to do that.
Right left, the L and the R. It's gonna
The what?
the L and the R.
The L and R, yes?
Yeah, left and right.
Yes.
Right, flip it. Right, left. It's gonna do the opposite of this one, right?
If we do VRL, that's what you mean?
Yeah.
Yeah. Now if we do down the VRL, that means, let's say what would going to be the result of that. Okay. Instead of doing VLR, we do VRL. Oh, you know what? It would be maybe nice to see it here.
Yeah, here. Okay.
Now in order, then we do right, visit, and left. What would be the result of that?
Should be the opposite.
So now we start here. We go right. Right? Next.
Go right.
Go right.
Right.
Go right.
Right.
Go right.
Yeah, no, right.
We visit.
Then there's
So this is the first thing we do. We visit this one. And then we go left. There's no left. Okay, go back. Here. Visit. Then go left. Right, there's a left. Go right. There's no right. Visit. Go left. There's no left. Okay, go back. Here. Visit. And then go left. So I'm going left. Okay, it says go right. Go right. Now right. So visit. And then go left. There's no left. Then come back and then visit. And go left. There's a left. Go right. No right. Visit. And there's no left. And we have done with this part. Then what I need to do? Visit now this route. And then go to the left. So as you can see, what is going to happen is that instead of sorting them from or displaying them from the smallest to the largest, it displays from the largest to the smallest. So LVR is that from the left, that gives you the smallest to the largest. RVL gives you from the largest to the smallest.
But doctor, here all the trees should be sorted in somehow.
Yes.
with
Yes.
the-
If-
doing the comparable.
Yes. If they're not sorted, we're not going to be able to do that. And that's bring us to how do we insert those nodes one by one and making sure that they are sorted. And that's the discussion we're going to be talking about, this insertion here. So how do we start? We start like with an empty tree. And then if we insert 15, well, then just add that to this becomes our root. Now this root would like to add 4, for example. What is going to be 4 is smaller than 15, which means it should go to the left. So that's why we have this. And then we add 20, so we add it to the right of this. But what happens if I have 17?
Should go to the right. Then
So I'm not going to be flipping around things. I'm just keep the tree as it was. I'm just going to, okay, normally I could just say, okay, 15 should be here. I could just do 15 here, so this should, sorry, 17 should be here, and then 20 on the right side of, so that's not how, this is not how it's going to work. Why? Because it's going to be too hard to implement this way, because the two different possibilities, and you're going to be having to deal with a lot of different kind of situation, and what is just going to be the rule is always, if it's bigger to the right, smaller to the left, and doing so we're not going to get confused.
so the first elements that I inserted, it's done yours.
It's become the head. Sorry, the root. Just yeah. The first element is the root. Yes.
17, he was in the left of 20.
Yes, because
Okay, if it was
But let's see how this works. No, it's not okay, because the rule is, when you take this number, you're going to see, is it greater than 15 or smaller than 15? If it's smaller, you go to the left. If it's bigger, you go to the right. So now it's bigger than 15, so we go to the right. But there's something on the right, so okay, it's 20. Is it bigger than 20, 17, or smaller than 20? No, it's smaller, so I'm going to put it on the left side of 20. Now this 19, for example, is it bigger than 15 or small? Yes, bigger than 15, so I'll go to the right. Smaller than 20, I go to the left. Bigger than 17, I go to the right. And that's why we have this. So that's the kind of rule that we're going to be using to easily insert things in that tree. Yes?
What if we put 250?
250? What do you mean? Two same number?
Yeah.
Well, then you have to decide in your implementation, is going to be, if they're equal, is going to be on the right or to the left. For example, if the question is, if the number is smaller than the value, then go to the right, else go to the left. So the else is going to include the equality. So you have to decide basically what you'd like to do. But it doesn't matter.
Equal or counted as a bigger? They are equal or-
Well, it depends on the implementation. It can be counted as going to the right or going to the left. Bigger or smaller, depending on.
So shouldn't be ignored, just ignore the reputation of the number.
Well, for now, we're not going to be dealing with that, because it's not really the main purpose. But you can just assume that if we have this to deal with, it's just going to be one of the. You have to make a choice. Are you going to consider when the values are equal to be to the left or to the right? It's just like a choice in the implementation. But it doesn't matter for us, even if it's right or left. At the end of the day, we just need to follow the rule. If it's greater than, we go to right, less than, we go to the left. If it's equal, well, choose whatever you want and be consistent. If you always put them to the left, we'll always put them to the left. It's not like sometimes you put them to the left, sometimes you put them to the right. That's what I'm trying to say. So that's why I'm saying it depends on the implementation. And let's have a look. Now, based on this, you'll tell me where is, when it's equal, going to go. Is it going to go to the left or to the right? So let's have a look now. So now, this is how we insert things into the tree. So we have this insert. You give me an element. I'm going to insert it. I'm going to call it with the root, because as you can see, insert is some kind of recursive. So we insert, and then we're going to start trying to insert it to the root.
How you add a root as an argument and there is only one argument?
Well, let's try to see this. Imagine that we're in 15. There's nothing. Root is null now, right? So I'm going to insert 15. I'm going to call insert with 15 and null, right? So it gets inside. This is 15. This is null. So P is null, right? Is P null? Yes. So I'm going to create a new node with 15, and P now is 15. I'm going to return this new node. So now this new node is this one. So now this root was null, but what I'm doing, when I'm done with this, it becomes a node 15.
What I mean is the method takes only one argument, right?
This one.
Public void insert.
Yes.
And here we call it with two arguments.
Because there's another one. This method is overloaded. You remember we did that when we were using, also probably some of you got that in the practical midterm. When we did some kind of recursion, or maybe trying to find the maximum in an array using recursion, or some sum of some elements of all the arrays in all the array, and then we called, if I remember, maybe let me just see if I can open some of the labs to show you what I basically mean. I don't remember which one though. I think it might be 6 or 7. There's no 7. 7 is today. source. Let's see which one. Not the. I don't remember though. Lab 6? We're in lab 6, right?
We have Fibonacci here.
In the Fibonacci? No, it was not in the Fibonacci. There's no, not one with working with arrays. Like this one here. When we started, for example, add all elements using like recursion, now we created this because every time we're going to call it with a.length -1 all the time. So that's why we just prepared this. So if we call this, we call it just with one, parameter, but the recursion occurs with this one because every time when we call the recursive one, we call it with the one that has two parameters. So this is the recursion one, and this is like some kind of a helper, just to help the user. Instead of always having to type this himself, we just put it for him because it has to be this. We want this to be the first thing we start with all the time because we like to start with the last value and then we keep going. So that's the main idea that we are doing here. Now every time if you insert an element, we'd like to insert it starting from the root. So that's why when the user is going to be calling this one, this is the one that is public, and this one is some kind of, it's not visible to everyone, only those that are inheriting. So we'd like this, so when somebody inserts, we'd like to insert from the root, and then we do the implementation that tries to then see what it's going to do with it. So when we call this calls this one, and then we execute. That's what I'm trying to say. So now let's just go back and see what we did. If we're in this situation, we'd like to insert 15. What happened is that we are going to call this one with 15. This one is going to call this one with 15 and null, because in the beginning the root is null, right? So this is going to be p is null and this is 15. If p is equal to null, yes, then I'm going to create a new node with 15 and put it in p, and I'm going to return p. So now this is the new root. It was null, now it contains the node p. So this is what we have done. So far so good, right? Now let's just insert 4 after we know that now our root has 15. Now when we insert now 4, the root is 15. So I'm going to call 4 with the root, which is going to call this one. Now the root is p. Is p equal to null? No. I'm going to go here and I'm going to compare el, this object that has 4. I'm going to compare to the key or the info of this node 15. So I'm just comparing 4 with 15. So based on your understanding, remember now with the compare to, it gives me a negative number, a positive number, or 0. If it's equal, it gives me 0. If it's smaller, which one is smaller? If the 4 is smaller, it's going to be negative. If the 4 is bigger, it's going to give me a positive. The main thing is that if you do this, you see, if you get confused with this compare to, I don't know, should I put like less than or greater than? Notice that the direction of this sign. If I do this, what I'm asking is this sign, like this one on the left, is it smaller than the one on the right? If yes, then I need to do something. If no, I need to do something else. Now again, this is 4, this is 15. Is 4 less than 15? Yes. Now if it was equal, I will go where? Now check this code. If it was 15, if I'm entering 15, is 15 less than 15? I'm coming back here. Is 15 greater than 15? No. So if it's equal,
It will just return B.
it will not insert it. So this implementation does not even allow insertion of duplicate values. If the value exists, I'm not going to insert it again. Well, based on this, what they did here with this tree, because now they're not I mean, the concern is not to have all the values even if they're repeated, just to have the value. If it exists, that's fine, we keep it. If it doesn't exist, we add it. So that's what this implementation is all about. But what if we would like to do that? Then you have to make a decision. For example, if you just remove this question,
Even the equal will insert.
now if it's greater than or equal, you're going to be here, you put it on the right. Or if you want to do it in the opposite way, just now flip these things. What I mean is, you swap these two, and then you remove the last question. So now, which means you're going to put them to the left every time if they're not there, or put them to the right. But this is not the discussion. It's based on you, what you like to do. Yeah.
Doctor, for this element that compared to
Yes.
key,
Yes.
what's the value it will give us if the element is 4 and the key is 15?
If the element is 4 and the key is 15, this whole thing is going to be
1
minus 1.
minus 1.
Because the one on the left is smaller than the one on the right, so it gives you a negative number. So then, this, because we're in this situation, this is going to be negative, so this is true. I go here, and p dot left, I'm going to insert, now check what is going to happen. I'm going to insert this 4 in the p dot left, and check what is going to happen. P dot left. What is p again? Remember, p was 15. So p dot left. There's p dot left is what?
No.
For now, it's null. P dot left is null. So which means now when I'm calling this, I'm going to call this one. Which means I'm going to call again this one here with 4 and null. Is p equal to null? Yes. You create a new node and then you put it in p and then you return it. Which means this now is going to create a new node with 4 and is going to put it in the p dot left that we called it the first time when the p was 15. And this is how this 15 is going to get, this 4 is going to get inserted to the left of the 15. Yes.
The key is constant.
The key is the like the info.
Will it stop every time you compare with the key?
Yes.
It will not change. It's 15. It will be 15.
For the node, unless we change it, yes. But the key is what we have here. Let me see. Now every node has a key and then a left and right. The key is the info that we used to do with the. And as you can see, this left and right is basically this node. Binary search tree is like a double linked list, exactly like the double linked list. Instead of calling it next and previous, we call it left and right. And actually, some double linked lists are called left and right. So some implementations of those use that. So that's the idea behind. Where were we? How to insert that. So we can, as you can see, we are using recursion to insert, to traverse a tree, and we have been using mainly all what we've seen so far in the beginning of the course, the lists, linked lists, and now using heavily relying on recursion because we'd like to be adding these things. But I'd like to make sure that I'm not sure if this example that I did was clear to you. Is everybody okay with the way how this code is going to allow us to insert anything? Now, can we just try, for example, what if we have this situation and I would like to add this 19 and see if we can just look through the code and not get confused with it. Can we try that? So let's try. Now we're going to insert 19, and this is our root, that is this one. And let's see how this is going to behave. I'm going to call insert 19, right? This is how the call is going to start. Insert 19. Let me just erase things, so I'm just going to start clean. I'm here. So I'm inserting 19. This is the code I'm going to call. This insert 19 is going to call 19 with the root, which is a reference to this 15. So this 19 root, is this equal to null? No. Now what I'm going to do is 19 compared to p.key. What is p.key? 15. Is 19 smaller than 15? No. So I'm going here. Is 19 greater than 15? Yes. So I'm going to call it now with 19. This is always 19. And p.write, which is the node that starts the 20. So now the root for me now, or the element, the node that I'm going to start with is this 20. So I'm going to call it again. This time 19 instead of the node that starts with 15, it's now the node that starts with that 15 is, instead of the node that starts with 15, is the node that starts with 20. And I'll get inside. Is this node n null? No. So now the question is 19 smaller than 20? Yes. So I'll get inside. I'm going to call left of the 20. Which one is what is the left of the 20? So I'm going to call now with this 17. So I made the first call that took me from 15 to 20, then from 20 to 17, then now from 17, what I need to do, I'm just going to call this to 17, is 19, well, it's not 17, is not null basically, and it's becoming too crowded here. Let me just erase everything so we can start, which is now 19 and then 17. Is 17 null? No. Is 19 smaller than 17? No. Is 19 greater than 17? Yes. So I'm going to call it again 19 with 17. What's the right of the 17? There's nothing. So I'm going to call it with null. And now while I call it with null, this is going to be null. I'm going to create a new node and return it, which means now this is going to create a new node to the right of the 17 with this 19, and then this is going to empty, this pop out of the stack and pop out the stack of the others, and everything is going to pop out, and then we're finished. So that's how I can insert that. Is that okay? I think it's kind of cold in here, but there's no way to turn this off. Yes? I'm sorry? When it will return what? D? P? Well, every time it returns. Now, because when we return something, we're going to return it to the call. Now, for example, when we, let's say, when we return something, we put it in either to the left, to the right, or to the root. Let me just maybe restart here. When we start with the first one, and then same thing is going to happen with the rest. When we start with the first one, we inserted 15 and it was null. So 15 null, we get this, and then we return now the new node. The new node is going to be now this return. Which one is going to be dealing with it? This one. So this is going to be our root. So this 15 is going to be the P when it's going to be returned. This new node when it's going to be returned, it's going to be the root. Now when this was this, for example, this is going to be on the right of this here. So when this is going to be called, it's going to get inside this again, and then it's going to return P. So this P is going to be stored in somewhere in the p.right or p.left, depending on which one here. So actually when I'm done, I'm going to return something all the time because of this return. This returns always something. I don't know if I clarified, answered your question. Qasim, what is means no. What are you trying to say disguised as a yes? Let's do it again. We have this. We have this 15, alright? We start with this 15. This, the beginning it was null. Okay? I'm going to call insert. This is going to call insert with null. This with 15 and null, right? Okay? Is this equal to null? Yes. P is going to be a new node with the 15. I'm returning P. So this whole thing is a new node with 15 that is going to be in the root. Right for now? Well, I'd like you to say clearly yes. Yes. A strong yes, not just like a weak yes. If it's not yes, don't say yes. But let's, okay, fine. Now if we agree on this, the rest is going to be exactly the same. Let's just, now we agreed on this one. How about this one? When we add 4. Now let's say we add 4. The root is not empty, so the root has this 15. And we're adding 4. So we're going to call this with 4 and 15. The node that has 15. Is this P that has 15 null? No. Is now 4 smaller than 15? Yes. So now I'm going to call again this insert. Now I have not finished, right? I'm just here. And from here, this is going to take me to a new call of the method insert with 4 and p.left. But there's nothing left, which means I'm going to call 4 and null. Now this new call with 4 and null, is P equal to null? Yes, it is. So I'm going to create a new node with this 4. I put it in P, and then what I'm going to do, I'm done with this. I'm going to return P. So this here is going to return P, which is a new node with 4. What am I doing with this new node with 4? Well, because this was called from here, now this insert is going to be returning the value that was returned before. So this is going to be this new node 4 that is going to be put to the left of this P. Which P? The 15. So I made 3 calls to the insert. The first return for P left. The second return will return this. Now this P is going to be returned and stored in the root, because the first one includes the 15. So we're always returning. That's how we get out. What do you mean minus of 0?
I need to insert minus or 0.
Minus 1, you mean? Like the value is minus? Negative number? It's the same thing. For example, if it was instead of 4, it's minus 4, it doesn't change. It's the same idea. It's minus 4 smaller than 15 or bigger than 15, and then you put it to the left or to the right.
What about 0?
Same thing. 0 is just the main thing here. We don't care about the values if they're positive or negative. We just compare. If this value is smaller than the one in the key, we go to the left. If this value is bigger than the one in the key, we go to the right. So that's the main thing. If it's negative or 0, it doesn't hurt. Is that okay? And that was the easiest part, because this was adding. Now let's delete something. When we delete, we'd like to keep things where they are. We'd like to keep the tree still sorted. And how can we do that? And now I need to get your attention, because if you're not paying attention, the headache is
The node.
I'm sorry?
Like we delete the node.
Well, it's not as easy. Let's see. There's some easy cases. Like for example, if I'd like to delete this 16.
Well, from the leaf, it's gonna be easy.
Yeah, exactly. From the leaf, no, not a problem. Okay, just remove it. That's it. We just need to make sure that this left is going to be null, and that's fine. But what if now it's something like this? It's not a leaf. Well, if it's deleting this now, I need just to put this to be like that. But there's some kind of decisions. What if this was, for example,
As a right or left.
something that has more than just more than just this. Well, this is not really easy to, like for example, like this one. Let's have a look at this one. Now I just would like to delete the 15, for example. I'd like to delete this one,
Where is the
Which one?
This one. the root.
yeah.
So how would you do that? Or maybe let's, instead of just this one, let's just this one. I'd like to do 10, for example. So you have to make some kind of a decision. Okay, what am I going to do? Am I going to, for example, replace it with the one from the left or one from the right? For example, here, if I'd like to delete this one, what should I do?
Which one is written here?
So that means you just remove this, and this 5 you put it here.
No, to the left. No, you need to.
What do you mean left?
You
No, it is easier. So if you keep another 12 in the center.
You have two options basically. You can take this 5 and put it here, or you take this 11 and you put it here. That means this becomes 11, this becomes 12, and this is gone. Oops, what happened?
But that you need to.
Or you just put it, as I mentioned, you just put this 5 here, and then you put 5 here, and then this becomes like this. Two options, yes.
But if you need to compare the information to maintain the sorting.
We need to make sure that to maintain the sorting, but in this case, if we take the left and put it there, it's going to always maintain the sorting. Or put it the right there, it's going to always maintain the sorting, right?
We want right, I call that's always right. Whatever
But can we, if we make a decision to make it right or left, is one of them going to mess up the sorting? So let's say if we take left, I put it here, and then remove this. Is the sorting messed up? No, it's still okay, right? And what if I do the opposite? I take the right. Now instead of this, I take 11 becomes here, and this becomes 12, and this is no more. This is still okay. So regardless if we take left or right, it's fine. If well, there's some kind of, maybe let's just see. I was trying to think about some situation that might be kind of interesting, with some numbers that are going to be maybe messing up some other things. But because of the fact that we're doing this sorting thing, if you delete one of the nodes, everything is going to be on the right, or on the left are going to be, for example, everything. Let me just remove this. Everything to the right of this 10 is bigger than 10, right? So even when you just remove it, and then it's going to balance itself. It's going to, I mean, keep the sorting all the time. So that's why if we delete, it's going to keep the sorting. So in terms of the implementation, is not going to mess up regardless which decision we're going to do, take from the left or to the right. But there's some situations that are going to be we have different options, and this is like you have different type of deletions with merging, and different type of how you're going to deal with that, and anyways, I just would like to find some better ways. And what if, for example, we decide to delete the root?
Whatever on the right of the road, we put it in the last clip of the right.
Now, if we just delete the root and you put to the right of the root, you see, you said, right, like for example, this becomes 30, right? And what becomes here?
No, you take the left. Hold the right and the.
Well, I understood that. Okay, let's say we delete this 10 here, this 15. What should happen now?
You should take the left.
Check the left to make it what? This is going to be new 10.
Yeah.
This is going to be 10.
Everything on the right of the road, you put it in the last element. The last element.
No. Everything onto the right here, you put it to the. Okay, so basically what you're doing is you're removing this, and then whatever here, you put it here.
Yes.
Why?
Because it will be all bigger than the left side.
Because this is going to be the biggest. This number is going to be greater than the number that is going to be on the left side here, and the one on the right side of the things, the nodes that are on the left side. Now, for this one, for example, I delete this one. Everything on the left is going to be smaller than the node itself, and any other numbers from the right. But the thing is, the biggest number from the left is the one that is going to be the most one on the right. So in this left side, the biggest number here on the left side is the one that is going to be on the right, all the way around, all the way to the last node. So that's why we're going to be, this is the big side. And this here is the result of, as you mentioned, when we delete this, you take the subtree here and you put it to the right of the nodes that are on the left. And what happens if we delete something like that have some kind of a tree, but from this side? Well, this is where it becomes interesting. Because now when you do this kind of thing, you end up with this tree, and this is not a nice, I mean, a kind of tree that you would like to end up in. Why? Because this is going to be just a tree that is going to be very long from one side and very short from the other side. And then if you'd like to find something quickly, it's not going to be helpful. So now by doing this, what you're doing is just making the tree become longer, which is not the best thing. But what you could do something different, and then making the tree to be some kind of balanced, or reduce the size, I mean the height of that tree, which is in this case what happened is that if I'm reducing the size like this is another option where we remove the 15, but instead of taking this and putting it on the right side of the one on the right, the one on the left, we just take this and put it on the right side of the one to the left. So the node that we are deleting, this one, if we go to the left, we need to make sure that you can plug it to the right. But what if this one has something? Has already something. So that's the kind of problems now we need to deal with. That's why this is not some kind of a very straightforward way how to deal with it.
Put previous photo. Yes.
This one?
There is, let's compare in 13 with the right and the left of 10. So let's make it after.
It's compare 15. I'm not sure to understand what is
13 with
30. This
the
one
right and the left of 10.
with the right
And the left of 10.
and the left of 10.
Like we said.
Uh,
Bigger than 11 or bigger than or less than 10 or bigger than 10.
to find out where we're going to put it. Is it going to be on the left and the right?
And the right, then we make it down. But the second one, I think we compare with. We didn't compare. We connect them directly.
I think you have to always compare, because now if you'd like to move it to the left, something that is coming from the right, you'd like to move it to the left,
Like this.
it has to be on the right side of the one on to the left. Why? Because the right side is the biggest thing that you can have on the left side. From this here, what I'm trying to say is that the highest number from the left side of the root is the one that is the leaf that is going to be the most right side in the left side of the leaf. This one, yes. So that's why this has to go below here on the right side of this one, actually, because it's the biggest thing that is available on the left side.
So we didn't access to 20 and 40.
We did not what?
Access to 40 and 20. We take only the 30.
Yes, because 20 and 40 are under the 30, so we don't change those. We just take the next one and then try to find a place for it. And because of this organization, we know that the others are going to stay in the same, respect the same condition. But the second thing is kind of different, because it's a different type. Okay, let's try to do the same thing that we did here. Now the second thing is that this one does not have a right side, but this one has. Now when we have a right side, it's kind of okay, take this, put it on the right side. But when we don't have a right side, after deleting this 15, I cannot just take this and put it here. Can I?
If it's smaller, we go to the 5.
Well, I can, basically, because this is much what is going to be doing. This 30, it's just I didn't find a way to represent that easily. So this should be on the right side, and we remove this thing,
So we have
and this gives us this. But this cannot be always available, because here the right side is not available. So when the right side is not available, what you should do? Well, keep going until you find a spot on the right side on the left side. But what I'm trying to just to say is that it's not as easy as just, this kind of adding. Even the adding itself is requiring some kind of gymnastics a little bit, just to be able to understand how this works. Now to come up with the deletion, it's just, as you can see, there's more different type of deletions based on the different type of solutions that I have. And now we're looking at this deletion by merging. This is the thing, and there's the deletion by copying. And let's have a look at this code here and try to understand what this code does. Let me just I want just to clear this. Now let's have a look at this code. So well, I'll just like to have a look at the code and see what this is doing. So imagine now we're going to be deleting one of the nodes. I just want to have an easier way to represent those. And you know what, let me just see if I can have the code on NetBeans here. Let me open. Okay, so this is the class, and we have delete. And you see this delete as compared to the insert is kind of more of thing to do. So what I'm going to do, let's see, I'm going to do this source format. No, because the comments are here. These are the ones I would like to change that because I want to make it shorter. So let me just do this. I'm just going to check these. I'll put them just here. The advantage is I'm going to just shorten the code a bit, and so the braces are going to be on the same line, and here we go. So now let's have a look at this code, and let's have a look at these situations that we were talking about, like this each one of those. Sorry. Now imagine I'm going to delete this 16, right? So that's the node I'm deleting. Okay, let's see how this is going to work. So I'm just going to call this method delete 16, which is going to delete and start from the root. So which calls this one. Is this equal to null? No, because I'm here. I'm deleting 16, I'm starting from the root. So is 16 less than 15? No. Is 16 greater than 15? Yes. So I'm going to delete 16 with 15 dot right. What is 15 dot right? So 20. So I'm going to delete 15 and with the node that has 20. Again, we call again. I'm going to go up. 15, 20. Is it null? No. 15 smaller than 20? No. 15 bigger than 20? Yes. I'm going to delete 15 and to the right of 15, which is right of 15. Well, so I was saying a mistake because I was saying 15 and everybody was just happy with whatever I say and they say yes and keep going. So please, let's not lose the focus. So we said 15, we went to the right. Now 20 now. So is 16 smaller than 20? Yes, I'm going to delete 16 and I'm going to go from the left. I'm going to delete from the left. So let's just go from the left. So I'm going here now. So now this is, I'm going to call with 16. So I'm just delete 16 and the node is 16. Is 16, is this node null? No. Is 16 smaller than 16? No. Is 16 bigger than 16? No. I'm here now. So now the key to be deleted, we found it. Is the left of P. What is P now? This one here. I mean this node here. Is the left is null? Yes. So I'm getting inside. So if it was left null or right null, I get inside because I need to do something. So now if the left is null, this is my situation. I get here. And this is true. The left of this 16 is null. So what I'm going to do, P dot right, which is null. Now remember, this is P. P dot right is null. I'm going to put this null inside P, which means this should be null now. I'm just deleting the node. This is going to be null. Why null? Because remember, this is going to be the P dot right of the 20. The right of 20 now becomes null. Because when I'm doing this, what happens? Okay, just finished here. There's nothing to do. Nothing to do. Return P. But return P because this was called by 20 dot right. So the 20 dot right that called one of these, well, this is going to be returning null. And I'm going to put the null in the first node that was before the one that I'm deleting, which makes this now becomes null, and I delete that.
So I have to find the null if it's in the right or the left.
What do you mean?
Put it inside 16. I mean, we search for the left and the right of the 16. there is none,
Okay.
we delete.
Well, no, we're just looking at this 16 that we would like to delete. Does it have any children? Because it did not have any children, it's kind of the easy way. That's why when we don't have this, there's no more children. So the key, okay, it's very easy. Just return, make it, put all the children. If it had some, even if it has some children, we just take those children and put them, just link them to that new node on the left.
We go to the last section.
Like this one, for example. If we deleted 20, let's see if what happens with 20. But first of all, just with this one, I just would like to make sure that everybody understands what happened. If we delete this, the node that has, like, it's a leaf, no children that this 16 has, it's kind of, this is going to be called, but I'm not sure if everybody got it. Yes. What I was thinking about doing, okay, what I'm going to do, you know what, I'm going to insert that, and then what I'm going to delete here, I'm going just to put this like this, so I'm going to follow the deletion. Okay, maybe just what I'm going to delete, I'm going to start from here, and I will just follow the deletion. How about that? Let me just run this. Now this file, if I'm running it, this is going to show me this insert in the binary search tree. I'm going to insert the elements one by one, and I just would like to make sure that in order for us to have an idea about exactly what happens, I'm going to insert these values. So when I'm inserting these values, I don't care now about the insert, because every value is going to be, now if I start with 15, then 4, then 20, then 16, I'm going to end up with this same structure, regardless of, if I start with 1 and then 4, well, then it's going to be kind of different. So let me start with 15, so I can have the same kind of structure. Okay, and I'm going to the options. Yeah, I just would like to, because I'd like to confirm that we have that. I'm going to display them in order, so I can see them, these numbers, like in this 1, 4, 15, 20, 16, and then 20. So let's insert now first. I'm going to insert 15, and insert 4, and then insert 20, and then insert 1, and then insert 16. Now if I display them in order, 1, 4, 15, 16, 20, and that's what we have, right? 1, 4, 15, 16, 20, and these are the ones that are in order. Now let's delete the 16. Where is the delete? Delete an element 3, and I'm going to delete 16. So when I'm deleting the 16, let's just have a look at this one. Delete the 16. I'm just going to see this case 6. What is going to happen? Oh no, not 6. It was 3, right? So it's just going to call this with the number that I just typed. So it's just going to call this delete, which is this one, and this is where we're going to stop. But you know what? I made a mistake. I did not start with this. I think I did not start with the debug. I started with this one.
Yeah, the number one.
So that's not how it is going to work. So I'm going to start again, because this is not going to stop here. I'm going to run it again with this one now. With this one, it will allow me just to see the different calls and see the different variables and also the output. So I'm going to insert them again. So we said 1, 15, 1, 4, 1, 20, 1, 1, 1, 16, and just let's print them just to be happy, to know that we have these values. Now I'm going to delete and 16, and here we go. Now we're here. Now I need your attention so we don't get confused, okay? Because I cannot go back. So I'm going to step into with this F7, because I would like to get inside and see what this is going to do. So F7 is step into. When I don't want to get inside, I'm going to press F8. So here I want to get inside this to see what is going to happen. Now what is inside of element? You can see that, right? 16. The root is, this is a root, is a node that has a key. What is the key? 15. And on the left there's another root. What is the one on the left? 4. And on the left there's another node. What is on the left of 4? 1. Right? This is what we have. Left of 4 is 1. And then onto the left of 1, I mean, sorry, this is the key. The one on the left is a node that we said. On the left is null. The right is null. So 1, there's nothing on the right or the left of 1. And this was the left of the key that was 4. On the right of the 4, there's nothing. So we can see now this is the representation of the tree, and that's fine. We're happy. Let's get inside. F7, because it's much easier for me. Now I'm getting inside. Is this going to be null? Obviously it's not null. So now what I'm comparing is 16 smaller than 15? No. Now I pressed F7, so I'm getting inside the compare to. I should not have. I'm just going to go outside. Okay, go back. Okay, I just need to press here. Is this one 16 greater than 15? Yes. So what I'm going to do, I'm going to delete now 16 from p dot right. What is p dot right? P dot right, that's 20. Okay, so let's do it again. But notice now I deleted another stack now entry for because the other call I'm deleting 15 from the node 20. Now is this 20 null? No. Is 16 smaller than 20? Yes, 16 is smaller than 20. That's last time we checked. It's like that. And now we're going to go to the left, because what we did here, we started here, we went to the right, and then now we need to go to the left of this 20. Okay, so we're going to go to the left, and with this, the p dot left is going to be the 16, which is exactly where we want to be. Now let me press on the right numbers, on right key. So I'm going to get inside again. So I'm calling again with this to be 16, the element, and the tree, I mean the node is the 16. So now we're in the node that we'd like to delete. Notice now I have this representation that shows me that there was like some kind of recursion that happens here that is still waiting to be executed, because we went to the right of 15. That's why we're here. This is still something we need to do to continue from here. And we went from the left of 20. That's why this shows us also like this. So it just shows us that we went from the left to the right, and this still need to be continued. So we're going for that. So exactly, yeah. So now is 16 less than 16? No. Greater than 16? No. So I'm here. So p dot key is the key to be deleted. So now we're in the key that has to be deleted. I'm just checking now. Is there any child on the left of 16? No. On the right, there's no child. I mean, this is going to be true, but I'm just saying, is p dot left equal to null? Yes, but does this mean there's no child? So yes. So if one of them is true, I'll get inside. This is true, basically. I'll get inside. Is p dot left is null? No, I'm just checking to one to the left. Yes. Then what I'm going to do is check this. What is p again?
16.
16, exactly. And I'd like to be able to display, please. Can I? Yes. I just like to show that on the right of 16 is null, on the left is null. And what I'm going to do now, this null is going to be put inside of the node 16, which means this becomes null. Okay, let's go. This is null. The next thing that happens, I'm going to return p, which is null now. So this null, what am I going to do with it when I'm returning it? Which call called? You see, remember we were in the right of 20. the right of 20 before. Now we were, sorry, left of 20. Sorry, yeah, you're right. We were on the left of 20, and this left of 20 sent us to this node 16 that we had to delete. Now we're going to be deleting this. This is going to return null. What I'm going to do is this null. Notice now I'm going to pop from the stack because I just finished a call of this delete. So I'm going to go back to this one. Which one is this one? I think there's something that I can see the calls, but I'm not seeing them. It's going to be much easier. Let me, if I can show them, it will be better. Window, debugging, call stack. These are the ones, and maybe the threads. No, there's one of the windows. This one. Let me see, there's one that I'm looking for, but normally yes, if I click, it should take me, show it to me which one is which, but I'm not seeing it. Let me just make sure that I'm not doing something. This is the session, no, that's sessions? No, I think that's the one that I'm looking for, but I just would like to make sure that I'm seeing everything. Debugging sources, no. So yes, anyways, I was hoping that it's going to show me, basically, if I click on this one, it's going to show me which line is going to be the thing, but probably no, it doesn't. Oh yes, I have to double click. Okay, I have to double click. So now the next, see, I was here. I'm going to return this. When I'm going to return this null, I was here. That returned the null. That means now this one is going to be null. And check now what was the node that was the on the left of it is the 20. See, so the p left, the 20 left is going to be null now. So that's what I wanted to just confirm. This is the one that I was looking for. Yes.
I think in second, so up, yes. If there is there is on the right there is none, on the left there is a number. This will go down.
Well, let's check that later. Okay, so let's not get confused. Let's just finish with this one, and then we're going to do exactly that question there later.
There is 4.
Let's just do that later. Because now don't look at another type of situation before even making sure that this one works the way we want it to be working. So that's why I wanted to make sure that the first one, this one works. Now we are here. The next thing is going to happen is that the left of the 20 is going to become null. Let's do that. Now see, now this is what is going to happen. This is going to be null, and then if I just go to the next, now this p dot left, what is p? Is the 20, and the left of 20 now became null, which means I officially deleted the left of 20. And then what is going to happen now, look, I have to return something. What is this p? Is the 20, and then I'm going just to put it to the right of okay, but yeah, I need to double click here actually to put this on the right of, to see it 15. So that's what is going to happen. So it's me double click here, so I can go back here and continue doing whatever I'm doing. So now we're going to go back to the right of 15. So this is going to return, now this is the node, the 15, with all the left and right now updated, and it's going to be, the 15 is going to be my root. And what I did, I just deleted the node that is in the leaf. And if I'd like to display that, display them again, this it was 6, right? So here I'm just displayed 1, 4, 15, the 16 is gone, and have 20. I'm sorry? Why is 16 is what? It's gone? We deleted it. And because it just came, we just deleted it. That's why. So this is what happened. Now let's just have a look at what the situation when he said that what if it has a child, the one that we deleted, right? like in this case. So let me add this 16 again. So if I add 16, it's going to be at the same place, right? If I see it, let me see it. You see 1, 4, 15, 16, and 20. Now let me delete the 20, because this is this example. If we delete the 20, let's see. We're debugging, we're still debugging. We haven't quit debugging. We still see this is still with these buttons here. That means we're still debugging. So now if I'm deleting the 20, okay, I'm here. I'm going to start from the root again. I'm deleting 20, starting from the root. This is going to get inside. Is the root null? No. So I'm going to compare. Is this 20 bigger than smaller? This is asking, is 20 smaller than 15? No. Is this is going to be 20 bigger than 15? Yes. So I get inside, and I'm going to delete now to the right of 15, which is the 20 basically itself. So let's get inside, and now I'm getting inside again. And the node now is the right of 15, which is the 20. So is this null? No, it's not. Is 20 less than 20? No. Is 20 greater than 20? No. So I'm here. Now I'm going to ask, is the left of 20 null? No, it's not null. As you can see, there's a lot of different things. But the right is. So one of them is null. I'm getting inside, so I'm getting inside now. Now I'm checking, is the left null? No, the left is not null. Right? So this is false. If I just select this and put it, now this is false. So now this is going to go to the else. So what is going to happen is p.left is going to be p. p.left, this one, is going to be p, which basically just, this is going to be 16, and that's what I'm doing. This is what p.left is going to do, right? I'm going to replace the node with the one to the left. That's what we wanted to do. No? But some say no. But it's not null, because if it was null, we'd be here. But this is the left of. Now, what is p again? Let's not get confused. What is p? P is 20. Yes. So the left of 20, is it null? No, it's not null. But I'd like to delete this one. And if the left is not null, what we do, check this, put it here. And then what should happen here? Of course, we need to delete this one, because we just put it here. So this officially deleted the 20 and put the 16 on the right of 15. What's the problem? Let's go back to the code. Now what we did, let me just erase this so we can just follow the code. So we're here, this is our p. And then we're asking, is the left null? No. Is the right? So this is false. So I'm going to go to the else. If the left is not null, what I'm going to do, take whatever is on the left and put it inside of p. So what is on the left? This whole node 16 is going to be in p, which means basically this that was on the right side of 15 will become this one. The same thing here. Now we have not done this. This connection is not done yet, because all what we did, we just in this parameter here p, we just put it now to be the node 16. But let's see this at work. When we're going to do that, we're going to return p, but to return p, to put it where? I'm going to put it to the right of 15. So that's why this is going to put it on the right of 15, and this 15 put it as a root. And if I display 6, right? Let me just, yeah. So I have 4, 1, 4, 15, and 16. The 20 is gone. Yes.
And if you have a child, two child.
Well, we're going to do that. Well, we'll take an example when we have some kind of, like this one, for example, right? And
Bigger.
it's bigger, but we can take it. Let's now, can I delete everything and starts from scratch? No, just better stop and starts from scratch. Okay, so I'm going to start again, and this is the output. Let's try to add this tree. So I'm going to add 1, 15, 1, 10, 1. No, because I want to start with 15, then 10. Now, by adding 15 first, I make sure that this is now the root, and then I add 10. So I'm going to add to the left of. Now it doesn't matter the rest. I can just add them as long as they're going to be in this order. So they're going to be added next to each other probably. So what did I add? I added 10, and oh, so sweet, it displays it for me. And then I'd like to insert 11. Which one? 5. Let's insert 5. And then let's insert 11, 12, 13. No, 30. And then 20 and 40. Okay. I did not realize that this is displaying, which is nice. So I can see that this is the tree, right? Now let's delete. Let's delete which one? This 15. Or you want to delete something else? That's nice, because the rest are kind of easy to manage, but let's do this one. Or you want to, anyways, let's try this. Let's delete now. So 3 and 15. Let's put this to be smaller now because we'd like to focus on the code. Okay, now I'm going to delete 15 from the root we start, and it's going to be immediately the root is null? No. Is this equal to, less than the value? No. No, this is not what I wanted to do. Let's go back. And is the 15 greater than 15? No. So I'm in the key that I would like to delete. Now, is the left null? No. Is the right null? No. So we're in the situation where we're not going to go here. We go to the else. Now, what is going to happen? Now, we're going to go into this get the min node. Okay, what is this? Get min node is a new method. Let's get inside of it. This is taking a node. It's just going to go to the left, go to the left, go to the left until it's null. So basically, what is this going to do? This is going to go to the left, go to the left, go to the left until. So basically, it's going to give me this 5, right? So let's just see that this get min node is going to return a node that is going to be the smallest node, and the smallest node from from where? From the right of the p. P is our 15. So basically, we're not doing this here. We're doing this from here. So from the right here, we're just going to go to the left until we find the smallest one on the right side. Now that we have found the smallest one on the right side, we're going to take this and put it in the key. So we just take the value and put it in the key of what? Basically, we just take this and put it here. We just put the 20 there, the value, because this P normally, if I just click on this plus, I just probably should okay, let's just try to be fast if you can. Sometimes it doesn't work. Okay, let me see it from here. Variables. If I have P, this is the key is 10. Why the key is 10? Why is the key 10? The key is 10? No, this doesn't. Is the key 10? No, this should not be 10. Did I do something? What did we execute? First we started from okay, we started from here, and then we went to here, and then we're going to be, this should be 15, and then I don't know why this is now showing 10. I'm getting confused. Let's stop. I'm going to do something. I'm going to run it again, but this time, instead of me wasting time trying to display it, I'm going to leave the values there. So let me add this 15 again, 10.
Quit.
I quit.
Yeah.
Good for me. So I have to do it again. Okay. I don't want the code now. I just would like to put the values. So let me insert this. We have like 15, and then 1, and then 10, and then 1, and then 4, 5, and then 1, then 11, then 1, then 12, then 1, then 30, then 1, then 40, then 1, then 20. So that's what we'd like to have. Now 3, we delete 15. Okay, what I want to do, so we don't get this problem again, I just would like to have this P, and I can pin it here. So now this is going to stay here all the time. Oh, why is it? There's always something. Okay, let me just take this, maybe. Okay, move it around. Can I move it around? No. Not move it around. All right. So anyways, this is the 15. I'd like to make it stick like this. So I'm probably move it around. Normally it should just move around, but if I put the plus, make it bigger than move it. Okay, let's try that. But I think it's just stuck to wherever it was originally found. Anyways, doesn't matter. As long as I can just do this, I will see it, no problems. Now it's 15. Let's keep going. So is 15 less than 15? No. Greater than 15? No. We find it. Is this null? No. Is this null? No. So we go to the else. We're going to find the minimum from the right. So the right, I'm sorry? P dot right is 30, yes. So now we're going to find among the minimum node on the right side of this 15, which should be 20. Now after I press on this, now this temp should be the 20. Okay, so I found this 20. So now this 20 is going to be put inside of the node, and this is where this is 15. That's good. So now the key is going to be 20, and now let's check what is going to happen on the right of this, which is this one here. I'm going to delete the key. What is the key? Temp.key? The 20 from P right. Which one is the P right? So I'm going to basically, I took this 20, I put the value here, and I'm going just to delete this node here. So this is going just to call from the p dot right, which is p dot right is going to be 30, is going to try to find the, because I'd like to delete this 20. So let's get inside, and now is this 20 less than 30? Yes. So I'm going to get inside and delete from the left. And then what I'm going to delete from the left, I'm going to be is the 20 less than 20. No. Greater than 20, no. So now I found it. Is on the left of 20 null? Yes. Right null? Yes. So I get inside and just p dot right. What is p dot right? This is null.
Null, yeah.
It's going to be null. So I'm putting the 20 to be null now.
Yeah.
And this is going to be returned to the left of the 30, which is going to be returned now to, I just deleted this 20 here, and this is going to be, I'm returning p, which is going to be my root. And do this. So basically, now after deleting, I can still have, so this is now the 20 that was moved here and deleted from here. But what I had to do, from the right side, I have to find the smallest one and then put it there. This is not this,
Yeah, I know that's similar. It's a different.
because this is by merging, while this is by copying. This is the one that we're doing. A lot of fun, I know, but you get some kind of idea of what the, first of all, the, I'm sorry?
We delete them by what?
We did it by copying, because we just copied this and put it here. That's what we did basically, and then deleted this one. Well, I wanted to do the other case, but it's going to take some time. But I want you to, what I'm going to do is that I'm going to stop here because we don't want to have a lot of time left. But I will try to give you more practice next class, inshallah, so you can have more hand-on exercises on these things. But I hope that what I wanted to achieve today is mainly one thing, is to give you an idea about, first of all, what are trees, how do they work, and what are the things that are needed to be able to maintain those binary search trees, which is the one that we know that they are sorted, and how to insert and how to delete. And you've just probably seen that this uses two of the things that we've been using for some time, the comparable that we used and then we did not use much, but mainly the double linked list, because these nodes, each one is like it's a double linked list, and also the recursion, because we've been using the recursion a lot in this insertion and in insert and delete. So we'll try to do more practice, inshallah, next class. I'm sorry, this video is going to be very long and probably not easy to follow, but something better than nothing.